Thank you for moving on. We have next we have Thomas Giguere, identifying lunar lava flows through crater density analysis.
Okay, so determining, we're in presenter mode.
Yeah.
So determining relative emplacement history of lunar Mar basalts is critical for just constraining the moon's thermal evolution and volcanic processes. Kind of goes without saying. So various techniques have been kind of ferreted out over the years, starting with DCVL and more recent techniques use manual methods to capture location and diameter of craters. And it's necessary to avoid secondary craters, of course. And we're looking at, well, some of these methods can include multiple flows, so that can be a flaw. Ideally, when you want to determine the age of a surface, you want to know that it's a single flow, single basalt flow. And furthermore, past studies have identified erasures of small craters, which is generally thought to be a younger flow coming in, erasing small craters. And this characteristically appears as a knee on a CSFD plot, which indicates a decrease in the number of craters below a certain diameter. So in this study, we're looking at a broad range, a broad study area, a range of crater diameters, basically all of the northern Oceanus Procellarum area. So it's a large area. It's a lot of data. Stuart notwithstanding, most of us can't manually count craters that efficiently. Those numbers are impressive, I might say. So machine learning techniques are desirable. You know, can they really work and help us in this regard? So over the past decade or so, convolutional neural networks have been developed with deep learning algorithms that do object recognition and identify specifically impact craters. So these algorithms have improved over time, and we just saw 2 talks ago where further improvements were made over past algorithms. So, but it seems there are still limitations. We are going to run into these kind of things. I mean, first of all, these techniques were kind of developed and rose up through the computer science and database world without a huge knowledge base of impact cratering processes. So that can be a limitation. There's a little bit of a built-in bias there. Some of the problems we've all seen are unrecognized craters due to degradation, obliquity, or slope surfaces. Now, we've got a sample here on the right showing true positives, but also some true negatives, some possible secondary craters that were identified too. So these are all kind of problems we've dealt with and run into. Secondary craters can be either eliminated or included with these deep learning algorithms. And ultimately, all of these things affect the AMA, you know, so we're might not get an accurate age when these discrepancies are included. So in this study, we're kind of moving away from the AMA and just looking at the relative densities. You know, maybe try to simplify the problem a little bit, de-emphasize them. So using two data sets, an auto crater database, which I think most of us are familiar with, more details on that in a bit. And then I'm converting this to a uniform grid with the number of craters based on each diameter range. So empirically, we can look at, see if we can identify areas of similar crater densities that can inform us about what's going on with the past flows. Another objective is to determine if the areas of similar crater densities correspond to a past kind of fairly large study, Heisinger et al., 2011. And then my real objective is to ascertain whether single or multiple flows based on variations in crater density can be identified using this large crater database and a grid cell approach. So here's a sample of Northern Oceanus Procellarum. This is showing part of the data set from 400 to 850 meters. It's about 66,000 craters, all shown in red. Right away, we can see a variation in densities at these diameter ranges. We're going to focus on the white box coming up in figure 2. This is overlaid on the WAC DTM data. So our data and methods include crater detection algorithm, mainly out of Perth, updated with the Ultravox YOLO version 5. I guess YOLO keeps moving on and is.
They're on 12, yeah.
They're on 12. Okay, good, good. This was good for the time. This analysis, the database was built based on morning and evening Kaguya. I know at one point the group took a diversion to look at NACs, but NACs have such a variation in lighting intensity, it can be challenging to get consistent results. They kind of doubled back to Kaguya data. So the global database includes 234 million detections between 60 north and south, and includes craters down to 70 meters.
I'm going to ask an interruption question.
Yes, interrupt anytime, that's fine.
How did they merge the Kaguya data given that the morning and evening data are not cartographically controlled to each other? And so there are offsets between them, the ebb and flow, latitude and longitude, depending on where you are.
Okay, that's a good question. I will check into that. Yeah, so, and keeping in mind that in this case, we're using the data for new results and taking, trying best to understand all the idiosyncrasies like that. So.
Yeah, and that's
So
the
that's
problem
good to
that
know.
I found, especially because we're going to be working on something similar here. Not only that, but it's also not controlled to WAC is a different control system.
Mhm.
And that means that it's also, all of those are different from the Kaguya plus Lola DTM, because that's controlled from Lola, which actually is an absolute coordinate system, it defines the coordinate system, which actually I was going to mention Dylan, because my database is going to be offset from that somewhat. So there are all these fun things cartographically.
And I was chatting with Marley earlier today about the data she's working with, which is further offset. Like that might be diviner related, so.
It was a Caleb Facet's TCGEM dataset for this 2014 diffusion model, are offset from WAC.
Yep. So all of those aside, let's continue.
Yep. Keep that in mind. And yeah, so this data set, this for the initial part of this talk, we're looking at 300 meters and above, about 160,000 craters. And also a clustering algorithm was used to try to eliminate secondary craters, but you really have to keep an eye on that. So I converted this data to 20 by 20 square grid using these tools. So basically 16 individual grid layers based on crater size, diameter in 50 meter increments. So we'll see that in table 1. And then the count of the craters assigned to each grid cell. So, and then kind of ratio of the grid cells. So generally the numbers follow maybe a Neuquén production function. And this grid format, in my thinking, allowed us to compare each grid, kind of a ratio, so that if you see a diminishment or reduction of craters in a grid of a smaller diameter, that could imply resurfacing. So here's table 1, shows the craters per diameter size, progresses pretty normally. There seems to be something odd about 60 to 649, where it's not really, and so on. So possibly some resurfacing or picking up some secondaries that are not aware of. So the results, yeah, we did have the 16 crater intervals mapped as grids. We saw that in table 1. And the crater, basically the crater count ratio showed more variation for small versus large diameter craters. That probably reflects an uneven distribution. And small crater grid cell, small diameter grid cells located in the center of northern Oceanus Procellarum had low ratios when compared to outer portions of the Mare. So possibly indicating a lack of secondary craters in the center. Didn't look at the peripheral cells because they're partial cells. So we compared a subset of the crater database, 400 to 700 meters, to previously published count areas east of Mons Rumker. This is a very popular area, P58, which is where Chang'e 5 landed. A revised count area, which encompasses a uniform crater density, would shift area P58 on the north border and expand the area to the southwest. So if we look at the picture, basically, we're seeing crater density not really match the spectral area. And there might have been issues with the Clementine spectral area in the first place. I find it a little bit difficult to draw very distinct boundaries on the Clementine spectral data. That color, those color ratio images are not that straightforward. So this area might be comprised of a single flow or multiple contemporary flows. That's always a possibility. So this figure shows the density map in the background with kind of a redrawn offset, P58. So, and if you're not familiar, the way the 2011 study was done originally was a count area was defined, and in theory that count area applies to the spectral area. So this is the spectral area outlined. A count done here, and then this age is assigned to that overall count boundary. More discussion, a grid cell in eastern northern Oceanus Procellarum near the count area exhibits an elevated ratio over the smaller craters in the 300 to 350 meter range. So the count is reduced in that area. This could be a possibility of a resurfacing event. Or secondaries could have altered the count. Could raise the count of the 400 to 450 meter area. Changes in target material can also affect the difference. So this is where this area is located. So the darker color indicates a higher ratio. This is the overview, and we've got that blown up here. So it's a higher ratio value. So just kind of summarizing this part and working with the grid. So we can see variations in crater density directly from the craters themselves before even putting them into a grid. So I kind of question the usefulness of the grid. There are ways to improve that. So we could use smaller diameter ranges. The craters going into the grid process, or reduce the size of the grid cell to try to basically get at maybe flow boundaries, for instance. Of course, you can always double check the source data from the large crater database. And I thought also it might be, instead of coming up with our own intervals, use maybe intervals, bin sizes from a traditional production function, like Robbins or Neucom. These changes will ultimately allow us to better define the areas and find resurfaced areas. And I'm glad you interrupted, Stuart. I want to encourage that. I'm interrupting myself here during the talk. So, but wait, there's more. So, yeah, I just kind of say lightning can strike twice, not in a bad way, but in a good way, good ideas. So, you know, I've kind of been thinking about these large crater databases and what they can tell us besides just age information. So, you know, so this thinking for me has been in 2024, but a decade earlier, somewhere at ASU, Lillian and Mark Robinson kind of worked on a similar approach. So nice to see. You know, I guess I could say I should have done a little more reference checking ahead of time, but these things pop up sometimes. Is this, maybe my excuse is this a paper? Well, it's an abstract. It's a little harder to find. I don't think they published other than that. So this work, let's look at it for a second. Aerial crater density analysis. So that's the key approach. So we're going to change our approach here just a little bit. Of volcanic smooth plains, and they're looking at Mare Imbrium. So AGU followed by an LPSC abstract. And they did a similar comparison to Hiesinger's spectral areas. So, and they asked the question, can an ACD be used to identify Mare locations with similar densities? Sounds familiar. And I think their ultimate objective was, well, neat, we have spectral information on the moon, but we don't really have that when we go to other bodies. So let's look just strictly at the density information. Mare Imbrium, El Rock Whack, Clementine, as we know, and then our old friend Crater Tools. And they looked at two different distinct spectral areas in Mare Imbrium. And these areas had a pretty large AMA difference that had already been calculated. So it's a good test case. Used a 0.5 meter diameter as their minimum. I added the color ratio data from Clementine. Just a nice example, you know, where it's very, here it's kind of easy to draw boundaries. And sure enough, their map is on the right, showing basically contrasting the blue and the red as they used N of 0.5 as quite a different crater density for those. So they've been pretty large bins to get that result. We're going to move on with our database, and so here's a basically an image of the 70-meter and up and larger crater diameters. Here's a zoomed in example of what we see with the data we worked with previously, 300 meters and up. And then when you add the 70 meters and up, you've got a whole different ball game as far as data. Fortunately, this kind of Excel-based data stands up to our modern laptops pretty well, so it can be used. Our little thing in the bottom obscures this, but so we're looking at continuous density variations here in NOP and what's it?
I can hide it if you want.
Oh, no, I know the numbers. It's 2 to 300. Yep. So this work might show smaller variations than what they did, kind of a gross comparison in the 2014 study with Ostrich and Robinson. So, but I think in the future, I'll probably slice this data to look at possible specific flows. So we see some examples at this scale. It's pretty large scale of dense areas with large craters transitioning into small craters. That's areas A. Here I'm using the laser pointer. That's actually moving from the larger craters, 300 to 400 meters, down to 100 to 200 meter craters, and the density is going down. So a possible area of resurfacing. And then we also see the influence of fresh craters and their influence on different crater diameters. Stuart talked about this in his talk just previously, and that's shown at area C. There's a bright fresh crater south of Mons Rumker that clears out craters all the way from 300 meters down to 100 meters. So, you know, a little bit hard to see, but due to the scale. But I think that's a fertile area for examining kind of the freshness of a crater, what type of diameter sizes are erased. Other things we can do with this large crater database is kind of just do feature identification. Here's Mons Rumker. It's a basaltic dome, so basically the same material as the surrounding lava flows, but it does show a lower crater density. Here's an interesting feature, Rima Sharp. So a depressed area stands out quite nicely in the crater, just a crater density map. Here we see it with just craters and the GLD 100 DTM data, and then a WAP image of that area. There could be a couple of causes of this besides just age and material type. And I think just kind of wrapping up the density map action here. We see variations in the density map based on small and large craters. So on the left is small craters dominating some of the young Mare, like P58 here. So fresh surface, or relatively fresher Mare is going to only have the small craters be prevalent. Whereas when you go to the larger craters, larger than 1 kilometer and up, you know, we have very little very low crater density.
Sorry, light pink is low and dark purple is high?
Yep.
Okay.
Yep. Should have added a legend. Thank you. And then large craters are prevalent in the older Mare, as we'd expect.
That's 5 minutes left.
Thank you. So I think that's time to wrap up with our second summary, but this is really high level. You know, so with these automatic crater databases, we've got 8 million craters to play with, provides massive amounts of data. But is this just data? Can we get any information out of it? You know, and I think so. I think these slides I've shown give us a hint at that, but I don't dig very deep into that. I think we'll be spending more time on looking at the promise of this data set and other data sets like it. But of course, we've always got to know the pitfalls with these large databases. So open for your ideas and questions. There's a lot more to do here.
So 4 minutes for specific questions for Tom, and then into break and discussion. But I'm going to hand this back to Stuart because it's difficult to take questions when you can't see people in the room and things like that. But thank you.
Veronica to step in because I should not be moderating myself. And we care to know what continuity. So thank you, Veronica, for stepping in, even though you're remote today. There was one question online. It was tangential. Does there exist an ancient lava flows to lunar map? And I responded, not that I know of, other than the ARIA in general, that map, which is available at USGS and Astropedia. I'm not sure of anything else.
Yeah, something that focuses on ancient Mare. I mean, first we have to kind of define ancient. I mean, for the global work, I mean, the Hiesinger does lay out from young to old, and could be argued everything is ancient. You know, when you're getting above 3 billion years in age. So I would refer you to that.
See nothing else online for the moment. Do we have anything else in the room? Toward the end of day one.
Later in the afternoon.
Yeah, I'm gonna ask a question that we might say, let's save it for the discussion. My question is, and this underscores, I think, a difference between my talk and the other AI ones that have been presented today, is when is what the AI does good enough for what we want versus not? So, for example, I'm taking a very conservative approach, whereas I think all of the other applications are more liberal. So for example, in some of your crater spatial densities or the dot plots of where they are, like I noticed there were a lot of craters like on the north and the south rims of larger craters, and just sitting there, and I would suspect those aren't real craters, that is an artifact of the yellow fine detection. And so this is where it's more perhaps again of a discussion as opposed to a direct question for you, and we might want to wait. But I'll leave it
Yeah.
out there.
I would agree that, and, and due to the problems that are known in these databases that you pointed out and we hear over and over at the PCC, I've really made a concerted effort to move to, what applications can we still do, knowing the limitations. So yeah, these probably should be documented and maybe that's part of the metadata. You've got a database with millions of craters, okay. List what the known issues are. Don't just give us a confidence value. Because that, we need more specific information if we're gonna get into the geology of an area. So to be continued, yeah.
Yeah, well, so
One more there.
And Adrian asked online, will collapsed lava tubes openings be interpreted by craters as craters by AI? And my response was, it depends. I mean, clearly was in some of what I did with those those pit craters. I haven't looked closely at the game work to see if those also identify lava tubes.
Yeah, your method would eliminate them because you're looking at it.
Yeah.
I think Lagain would include that. And one thing I didn't point out between the 300-meter and up database is that they put a little more rigor into it by including depth. Because that was a resolution, kind of the cutoff, where they could compare, they captured the depth for each crater. So by doing that, number one, they could eliminate positive features because, yeah, to his point, yeah, positive features, domes are included in the crater database. That ain't good.
Seeing no more questions, I'm going to say thank you again. And that ends this session.